We're going to be starting lecture 2.1 through 2.5 here today, where we're going to be starting to talk about some chemistry. So we're going to talk about atoms. We're going to be introduced to the atomic theory. While we're at it, we're going to learn about the most common tool that's used by chemists. That's a periodic table. We'll learn all sorts of things about that periodic table, and there's lots of information that it gives us. We're going to start learning about what information we can get out of it. Then we're going to start talking about compounds, beginning with molecular compounds, then ionic compounds, and we'll talk about formula determination while we're here. Okay, let's get warmed up with a little bit of review, and our first question asks, which of the following are exact or are they measured numbers? And the oldest known flower lived 120 million years ago. Is that an exact relationship or a measured relationship? That's actually measured. There's 1,000 milliliters in 1 liter. Is that an exact relationship or a measured relationship? Well, that's an exact relationship. 2 units in the same system is one of our 2 examples of exact numbers. What about there being 454 grams to a pound? No, that's measured. The metric system isn't based on the English system or vice versa. So they took a pound and measured it in grams. And how many significant figures do we have in 123.0? Well, the question is that 0 significant? Well, is it telling us how big the number is? No, it's not. So what's it doing there? It's actually known, so that is significant. What about 100? Are those 2 zeros significant? Well, if I put my thumb over those, I no longer can tell how big the number is. So those are replacement zeros, just telling us how big the number is. 102,030,000 has how many significant figures? And that would be 5. The 1, the 0, the 2, the 0, and the 3. Those 4 zeros at the end are placement zeros telling us just how big the number is. And in 0.00010 we have 2, the 1 and the O at the end. The zeros to the beginning are telling us how big the number is. And how's 123 written in scientific notation? Well, first we write our foundation, so we take the 1, followed by a decimal point, the 2 and the 3, all times 10. Then, this number is larger than 1, so our exponent is positive. And we're moving the decimal place over 2. So 1.23 times 10 to the 2. What about 0.001234? Well, 1.234 times 10 is our foundation. The number is smaller than 1, so our exponent is negative, and we move our decimal 3 places. What is the maximum number of friends that could be fed pizza if each friend eats 5 slices and you only have $50? At the pizzeria you selected, each pizza costs $12 and has 8 slices. Okay, this is an example of a real-life problem which does not come with an equation, so we pretty much have to rely on our units for something like this. Well, we're starting with step 1. We're after friends, which tells us all about step 2. We're looking for a number with a single unit to start the calculation with. So let's see what number has a single unit. Is that just 5 slices, or is that 5 slices per something? That's 5 slices per friend, so that's 2 units. Can't start with that one. What about that $50? Is that $50 or $50 per something? I think that's just $50, so that's probably what we're going to start with. And then let's check out the other numbers. $12, is that just $12 or $12 per something? Per pizza? And at 8 slices, is that 8 slices per something? Also per pizza. So indeed, only the $50 had a single unit. Alright, on to step 3, where we begin by getting out of that initial unit. Can we go straight from dollars to friends? No, but as we look up at the conversion factors, we see dollars will take us to pizzas. Okay, well, let's go to pizzas. Not after pizza, so out of pizzas. Can we go to friends now? No, it looks like it's time to go to slices. Okay, we're not after slices, so let's get out of slices. Can we go to friends now? Yes, that relationship we do know. The numbers tell us $12 per pizza, 8 slices per pizza, and 5 slices per friend. And I come up with 6.67 friends. So how many friends should we actually invite out? Well, we want to make sure we can feed everybody. So 6. Do note how our units set up our problem for us. Gotta love units. Okay, here's a metric conversion. We're converting 37,400 nanometers to micrometers, and we're still using our units. So step 1 equals micrometers. That tells us everything we need to know about step 2. We're looking for a number with a single unit to start the calculation with. So that's the 37,400 nanometers. And here comes the beginning of step 3, nice and easy. Now comes the big question. Can we go straight from nanometers to micrometers? No, we have to go through the base unit, so into meters. Why? Because everybody relates to meters, so we're guaranteed we can get into meters, and we're guaranteed we can get out of meters. Now for the numbers. The base 10 number always goes where? With the base unit. So the meters get the tens, the nanos, the micros, the kilos, the gigas always get a 1. And 1 nanometer, like 1 nano anything, is 10 to the negative 9th. Whereas 1 micrometer, like 1 micro anything, is 10 to the negative 6th. Okay, we have 3 significant figures, the 3, the 7, and the 4. So here's our foundation. You can put this on your calculator or do as I normally do, which is convert our first number into scientific notation, and then when those numbers are multiplied, the exponents are added. When they're divided, the exponents are subtracted. Negative 4 plus negative 9 is negative 5. Negative 5 minus negative 6, of course, subtracting a negative becomes positive for positive 6. Negative 5 plus 6 is the same as 6 minus 5, or 3.74 times 10 to the 1. You can always put this on your calculator. But if you don't have one, what I just did is probably the easiest way. Okay, convert so many kilograms to milligrams. Step 1, we're after milligrams. Step 2, we're starting with the given number of kilograms. I hope step 1 and step 2 were easy. And I'm pretty sure the beginning of step 3 is easy as well. And we like easy. We're halfway through the problem before we get to any challenge. Now, can we go straight from kilograms to milligrams? No, we have to go through the base unit, so into grams. Now we can go to milligrams or any other prefix unit. Getting quick and easy. And now the base 10 number always goes where? With the base unit. So that would be the grams. And a kilogram, like a kilo anything, is 10 to the positive third. Or a milligram, like a milli anything, is 10 to the negative third. So that's 7.2 times 10 to something. Our original number is 7.2 times 10 to the negative 3. Negative 3 plus positive 3 would be 0. 0 minus negative 3 would be positive 3. Okay, how many deciliters does a 162 milligram sample of gas occupy if it has a density of 1.14 grams per liter? We are still using our units, so step 1 equals deciliters. Step 2, only one of these numbers has a single unit attached to it. That would be the 162 milligrams. And now step 3, out of milligrams. Can we go straight from milligrams to deciliters? No, we're going to go from mass to volume. How do we do that? Through the density term. So it looks like we first need to be in grams. And then applying the density unit, we can get into liters. And now we're no longer talking about mass, we're talking about volume, so we're nearly home free. Can we go from liters to deciliters? And you've got to love the base unit. Never more than one step away from any prefix unit. And those numbers, do note that 1.14 is going to go with the grams. It doesn't matter if it's on the top or on the bottom. For the other guys, base 10 numbers, still going with the base unit. So 162 times 10 to the negative third, divide 1.14, divide 10 to the negative 1. If I have any numbers that aren't all on base 10, I'm just going to break out my calculator from the beginning. or 1.42 deciliters, putting that in scientific notation, 1.42 times 10 to the 0. Okay, on to the atomic theory, which is essentially the theory that all matter is made of these tiny fundamental particles called atoms. Now, the atomic theory has been postulated since ancient Greek days, where the idea was you could cut a sample of something in half. Think of a piece of paper, you cut it in half, then cut that in half, and then cut that in half, and then cut that in half. And that eventually you'd be down to a point where you couldn't cut in half anymore. And at that point you've gotten down to the individual atoms. Well, the atomic theory states a few things, including that matter is composed of tiny fundamental particles called atoms, and that atoms of each element are unique and yet different from the atoms of the other elements. And what makes one element different from the others is the number of protons. Here's something important to remember in chemistry. What makes one element different from the next? The number of protons in its nucleus. This is purely and the only thing that makes one element different from the next. And the third thing is that atoms of different elements combine to form compounds. That's what the word compound means, made of different things, so different elements. And then when it comes to a chemical reaction, we're going to take what we begin with and separate it and then recombine it into new combinations. And so that means in a chemical reaction, atoms are never created, nor are they destroyed, nor are they transformed from one type into another. So what you start with must be what you finish with. And later we'll find that means we must have balanced chemical equations. But again, you take what you begin with, separate these atoms from each other, and then bring them back together into new combinations, which will be your products. Okay, the atomic theory essentially is stating that all matter is a collection of these tiny fundamental particles called atoms. And what I have here on the screen for you is what I call the Disneyland version of an atom. It's a nice simple model, but when we start talking more about the electrons, it's going to break down. But for right now, good simple model. Now, we are going to talk about subatomic particles, so I did mention electrons, and electrons, represented E negative, are these tiny little guys with a very tiny amount of mass and carry a negative charge, hence the negative with the E negative. Then we have protons, which are much larger, 1,835 times the mass of an electron, and they carry a positive charge, hence the plus. Most of the time we have neutral atoms, so the protons and the electrons would be the same. Lastly, we have neutrons, abbreviated N0, where that 0 refers to zero charge. There's no charge on a neutron. They are neutral. One way of thinking of neutrons is kind of like a proton and an electron that have combined together, and now they have no leftover charge. Physicists would argue with that, but in many respects it's a nice simple way to think about neutrons. Okay, onto the nucleus of atoms, and this is where the protons and the neutrons reside, and this is where the vast majority of our mass is. And so these tiny little electrons are spinning around this nucleus at tremendous speeds. And it should make sense that the big guys are in the middle and the little guys are flying around it. Just think about the planets flying around the sun. Now, I would point out that this nucleus is a tiny, tiny, tiny little fraction of the atom. If the atom was the size of a football field, the nucleus would be about the size of a pea. So that is a tiny little amount. So what is an atom? It's mostly empty space. I know that's a strange concept, but it's mainly empty space. Let me introduce you to the term nucleon, and this would be our nuclear particles. So that's the protons and the neutrons. And as I mentioned, the vast majority of our mass makes up the nucleus. Here's a new term for us, the atomic number. This is the number of protons in a nucleus, and this is what identifies one element from the next. If we look at a periodic table, we'll see all these whole numbers associated with our element symbols, and those are the atomic numbers, the number of protons. And again, this is what makes one element different from the next. So for example, all oxygen atoms have 8 protons. If you got 7 protons, you don't have oxygen. All carbons have 6. All chlorines have 17. We always have a periodic table to tell us how many protons. I want to share the term isotopes, where isotopes are atoms of the same element, but they're different in that they have a different number of neutrons. So if you ever heard an element name and then a number like carbon 12, uranium 235, that number is what's called the mass number, and that would be the total number of nucleons. So that would be the sum of the protons and neutrons. So they still would contain or retain the same chemical behavior, but they have a different number of neutrons. So they're still the same element. So neutrons aren't impacting which element you have. It may mean the difference between if it's a stable nuclei or a radioactive nuclei. I mentioned mass number, and that was that number that goes along with an element an isotopic symbol. So that chlorine 35 means we have chlorine with a mass number of 35. Carbon 14, that's carbon with a mass number of 14, where the mass number is the sum of the protons and the neutrons, and essentially what identifies one isotope from another. Now, this information isn't on the periodic table because this is specific for those isotopes. So don't go looking for the mass numbers on the periodic table. Now, I want to point out, I can give you the neutrons and then ask you about the mass number, or I can give you the mass number and ask you about the neutrons. In this example at the bottom, it says how many neutrons are in the isotope plutonium-239. Well, we look up the atomic number of plutonium and subtract that from the mass number, because the mass number is protons plus neutrons. Subtract the protons, and that gives us the neutrons. So again, I have to give you the mass number to ask about the neutrons, or I can give you the neutrons and ask you about the mass number. I have to give you one in order to ask about the other. Now, I talked about stable versus radioactive isotopes, and normally we would find stable nuclei within a proton to neutron ratio, neutron to proton ratio of 1 to 1 up to 1 to 0.5 to 1. We find at the smaller end of our periodic table, we usually have about a 1 to 1 ratio. As we get bigger and bigger and bigger and bigger, we tend to need more and more and more of these neutrons to hold the nuclei together. So we see it go up to about a 1.5 to 1 ratio. That doesn't mean that just by fitting within that ratio it's automatically going to be stable, but we do find that all stable nuclei do have a neutron to proton ratio within that range. Okay, let's answer some questions. Which of the following statements are true? A proton carries a positive 1 charge and an electron carries a negative 1 charge. This is true. They're essentially the same size, just one is positive and one is negative. So that's why when you have the same number of electrons as protons, you have a neutral atom. And a nucleus of an atom has a negative charge. That's false. The nucleus of an atom is where the protons and neutrons are, so it would be positively charged. And I didn't mention this, but an alpha particle is essentially a helium atom without its electrons. So if you join me in Chem 112 when we talk about nuclear chemistry, we'll be reminded that an alpha particle is simply a helium-4 nucleus. A neutron is an uncharged particle with a mass slightly greater than a proton. That's true. More than 99.9% of an atom's mass is in the nucleus. That's true. And all atoms of a given element have the same mass number. That is not true. All atoms of the same element have the same atomic number. Remember, the mass number can differ by isotopes. Okay, for any neutral element, the number of electrons is equal to the number of protons. That's true, to be neutral. The mass number is the sum of the number of protons and neutrons. This is true. That's a definition of mass number. Isotopes of atoms contain the same number of protons but a different number of neutrons. This is true. This is pretty much the definition of isotopes. And the atomic number equals the number of protons in an atom. That's right, and that's what identifies which element you have. And what makes one element different from the rest? The number of protons in the nucleus. And how many electrons, protons, and neutrons are found in a chloride ion formed from chlorine 35? Well, let's do the easy one first. Number of protons, we look at the periodic table, and the atomic number is 17, so protons is 17. We have a -1 charge, which means what? We lost an electron? No. Negative means we have one more negative than positive. We gained an electron. We gained a negative. Positives or negatives are formed by losing or gaining electrons. Don't ever try to change the protons. Remember, that would change your element. And then lastly, how many neutrons? Well, our mass number of 35 says 35 protons and neutrons. Subtract the 17 protons, and that gives us 18 neutrons. So again, that was 18 electrons, 17 protons, and 18 neutrons. Okay, onto the periodic table, which is this wonderful tool that chemists always have available to them. So expect you'll always have this available. When you get your exams, you'll essentially have a periodic table. Okay, now it's called a periodic table because it's the arrangement of elements by similar chemical and physical properties. So we tend to see this repetition of similar chemical and physical properties. Let me share some terms with you. I hope you have your periodic table pulled out. And we have groups, sometimes called families, and these are the vertical columns. And we find that they're called families because they share similar physical and chemical properties, hence the term families. Again, these are vertical columns. Then we have periods, which are the horizontal rows, and this is going to be related to the buildup of electrons around the nucleus. And then we have the metals, which are located to the left of the zigzag in the periodic table. We have the nonmetals, which are to the right of the zigzag. And then we have the metalloids, sometimes called semimetals, which are directly adjacent to the zigzag. And here in green, we can see the metals. In blue, we have the nonmetals. Note where hydrogen is. Even though it's over on the left side, it's actually a nonmetal. In some periodic tables, it's above next to helium and above fluorine. Then in pink, we have the metalloids/semimetals. For the metalloids/semimetals, the ones on the right of the zigzag tend to have more nonmetal characteristics. The one on the left tend to have more metal characteristics, but they must have at least one of each. So for example, silicon is shiny, but it's brittle and it's a poor conductor of heat and electricity, which are characteristics of nonmetals. So shiny is a characteristic of the metals. Okay, onto the different parts of the periodic table. And I'm going to show a periodic table in a moment where we see the S, the P, the D, and the F block. I'll get to that in a moment. But when you look at your periodic table, we have the main group elements, which are the left and the right shoulders. These elements are very predictable, and we'll find it's because their last electrons went in the outermost shell. That's what makes them very predictable, and hence the main group elements. Then we have the transition elements, which are the guys in the middle. And then we have what are called the inner transition elements, sometimes called the rare earth elements, sometimes they're called the lanthanide and actinide series, and these are the guys at the very bottom. And then because they're so important, I want to point out the noble gases, which is your far right column, are essentially the chemically inactive gases. Everybody wants to react to change their number of electrons. Well, these guys don't want to react. So what might that tell us? That they don't want to change their number of electrons, and that's indeed correct. They have a very stable electron arrangement, and they're very happy with it, and this is why they don't want to react. Well, this is important because all elements are going to react in such a way as to obtain the electron configuration of their nearest noble gas neighbor. So we're going to determine which is the closest noble gas, and that's going to tell us what it does. Is it going to gain electrons? Is it going to lose electrons? Okay, so here's our periodic table, and there's the S's, the P's, the D's, and the F's. The left shoulder is the S, the right shoulder are the P's, the guys in the middle are the D's, the guys at the bottom are the F's. The left and right shoulders are the main group elements, the D's are the transition elements, and the F's are the inner transition elements, sometimes called the rare earth elements. And we'll talk more about the S's, P's, D's, and F's in a later chapter when we look at electron configurations more closely. Okay, let's see what we might do with some of this, and we're asked, what is the halogen in period 4? Where our halogens are our group 17 or group 7A elements. Period 4 begins with K for potassium, and so they would cross at bromine, element 35. So there's our halogens, group 7A, and the halogen in period 4 is bromine. Then the noble gas in period 3, remember our noble gases are that last column. And then let's just go down 3 to get to argon, which by the way is our third most abundant gas in the atmosphere. And now how many nonmetals, metalloids, and metals are in group 14? Well, let's see, in group 14 we see one guy blue, so that's one nonmetal, two guys pink, so two metalloids, and then 10 lead, and if we're going to count 114 would be metals. So carbon, nonmetal, silicon and germanium, metalloids, tin and lead, metals. And identify the nonmetals, metalloids, and metals in period 5. Well, period 5 begins with rubidium, and rubidium all the way through tin are our metals. Antimony, that's Sb, and tellurium are our metalloids, and then iodine and xenon are our nonmetals. On to compounds. Well, let me stop for a moment and mention that all chemistry occurs because elements are trying to change their number of electrons. So all chemical bonds are essentially elements trying to change their electrons. So chemical bonds are something to do with electrons. Now, how many electrons you have is based on how many protons, and hence your atomic number. That tells you how many electrons you would have, and then how many electrons you have would tell us, do you want more or do you want less? If you want more, you're going to try to gain electrons. If you want less, you'll try to lose electrons. And in compounds, we're essentially exchanging electrons in order to hold elements together. We have two types of compounds, molecular and ionic. Sometimes molecular are called covalent, and that's where elements are trying to share electrons. That's only going to occur between nonmetals, which are trying to gain electrons. Ionic compounds result when we have a metal, which is happy giving up an electron, joins together with a nonmetal, which wants to gain electrons. And now we really know what the difference between metals and nonmetals are. Metals want to lose electrons and form positive ions by having more positives and negatives. Nonmetals want to gain electrons, forming negative ions, or molecular compounds where they're just going to be sharing. Okay, now I already mentioned that all elements are going to react in such a way as to obtain the electron configuration of their nearest noble gas neighbor. Well, this is known as the noble gas rule. Sometimes it's called the octet rule because normally that would mean elements are going to try to get 8 outer electrons. We're going to find those electrons in the D's and in the F blocks. Those are buried in interior shells, and so they don't have those last electrons on the outermost shell. So the left and the right shoulder represent the electrons in the outermost shell. I want to share the term bonding number with you, and this is the number of electrons that are lost or gained when an element reacts. And from each group, we should be able to tell group 1 has 1 outer electron, and it's going to lose that to go back to be like the last noble gas. Group 2 has 2 outer. They're going to lose both to go back to the last noble gas. Group 13 has 3 outers. They're going to lose all 3 to go back to the last noble gas. You could also just grab an example. How about element 13, aluminum? Well, it wants to be like neon with 10 electrons. Neon is closer with 10 than argon with 18. So it's going to lose 3 electrons to have 10 electrons like neon. Group 14, they're going to have a bonding number 4. Some lose, some gain 4, but it's 4. Group 15, they want to gain 3, so bonding number 3. Group 16 want to gain 2, so bonding number 2. Group 17 want to gain 1, so bonding number 1. And if you're given an ion like the iron 2 ion, meaning iron with a +2 charge, well, there's your bonding number. Or if you're given the formula of a metal or a non-metal in its ionic state, that charge is your bonding number. Okay, we're going to be going with molecular compounds, and this is where we would have two nonmetals sharing electrons. That's what it means to be covalently bonded. So covalent bonds are the sharing of electrons, and this really is the epitome of sharing because each element increases their electron by sharing an electron. So atom A shares one electron, atom B shares one electron, and now they're both in mutual possession of that shared pair, so they both gain an electron by offering one up to share. Now the number of electrons that are shared is the same as the bonding number, and that's going to be the number of bonds that are formed. So for example, oxygen has 6 valence electrons, 6 outer electrons, and it wants 8, so it wants 2 more. And we can just tell that by looking at the periodic table. Oxygen wants 2 more electrons to be like neon. So it has a bonding number of 2, and hence it's going to form 2 covalent bonds. Okay, when it comes to a molecular formula, essentially I want to point out how we use a subscript to indicate how many of each element are in that compound. So in H2O we have 2 hydrogens to each oxygen. In sodium chloride, we see 1 sodium and 1 chlorine. In ammonia, in H3, we see 1 nitrogen and 3 hydrogens. And that last guy is sulfuric acid, H2SO4, with 2 hydrogens, 1 sulfur, and 4 oxygens. So the subscripts essentially indicate how many of each element are in that formula. Okay, now we actually are able to determine the formulas of many compounds, and to do so we would identify each element in the compound's bonding number and then write this above the element symbol. Above and between this, we write the least common multiple of the 2 bonding numbers. This is essentially the number of electrons exchanged if we're talking about ionic compounds, or the number of covalent bonds formed if we're talking about molecular compounds. Then you would divide each bonding number into that least common multiple, and that's how many of each element are in that compound. Let me do an example. And it's easiest to start with ionic compounds. So here we want to know the formula of sodium chloride, or the formula compound formed between sodium and chlorine. Well, sodium forms a +1 ion, chlorine forms a -1 ion, and hence they both have a bonding number of 1. Here's step 1, identify your participants and their bonding number. Step 2, our easy step, the least common multiple of 1 and 1 is 1. Now in an ionic compound, this is the total number of positives balancing the total number of negatives. So I have +1 balancing -1, so I only need 1 sodium for +1 and 1 chloride for -1. We're going to find that chlorine, when it gains an electron, is called chloride. Between magnesium and chlorine, well, magnesium forms a +2 ion, so it has a bonding number of 2. Chlorine still gaining 1 electron, so it still has a bonding number of 1. This time our least common multiple is 2, and that 2 is telling us something. That +2 is balancing -2. So we're going to need 1 magnesium and 2 chlorides. Now let's stop and look at this. That means we have +2 balancing -2. And in an ionic compound, the formula is going to reflect this charge balance, and we'll talk more about that later. What about between aluminum and sulfur? Well, you might see that aluminum forms a +3 ion, and sulfur a -2 ion, again, which are the closest noble gases to these elements, and that would tell you aluminum was losing 3, sulfur was gaining 2. Okay, there's their bonding numbers. Step 2, the easy step, the least common multiple of 3 and 2 is 6, telling us +6 is balancing -6. So how many aluminums do I need for +6? And how many sulfides for -6? Our last one is a molecular compound. Hydrogen and oxygen are both nonmetals. That's why we know that's a molecular compound. The rest of these were ionic compounds, and note each one had a metal in it. If you've got metals, we're talking about ionic compounds. Okay, well, still the same step one, hydrogen, oxygen, and there's their bonding numbers. Hydrogen has a bonding number 1, trying to become like helium, needs 1 more electron. Oxygen has a bonding number 2, needs to gain 2 to become like neon. Step 2, still step 2, least common multiple of 1 and 2 is 2. Now this time, this is the total number of bonds that are formed. So there's 2 bonds being formed. And since each hydrogen is forming 1 bond, we're going to need 2 of them. And since oxygen is already forming 2 bonds, then we just need 1 of them. And I think we knew that hydrogen and oxygen formed water, H2O. This is one of the most common things that chemists do, formula determination. So plan on practicing and mastering this, and that'll make your future chemistry much easier. Okay, just real quickly I want to introduce you to what are called Lewis dot diagrams, or structural formulas, where we're trying to illustrate molecules where we tend to show covalent bonds as a dash between 2 elements, or shall I say 2 atoms. So we see in hydrogen, each hydrogen wants to gain 1 electron, so they formed 1 bond, and each gained 1 electron by doing so. In water, hydrogens want to form 1 bond, oxygen wants to form 2 bonds. In hydrogen chloride, hydrogen wants to form 1 bond, and chlorine wants to form 1 bond. Now sometimes we need to form more than just 1 bond between atoms. So for example, in carbon dioxide, carbon wants to form 4 bonds, but it's only got 2 buddies to share them with. And so to get 4 bonds with just 2 oxygens, it's going to have to form 2 bonds to each. And do note, oxygen's got its 2 bonds. The carbon's got its 4 bonds. The next guy is acetylene, also known as ethine. And do note, for carbon to have 4 total bonds, because he wants 4 more electrons, he had to form a triple bond between the 2 carbons. We already had 1 bond going to each hydrogen, but we're going to have a triple bond between those 2 carbons. And if we look, hydrogens have their 1 bond, the carbons have their 4 bonds. When we're done drawing molecules, everybody's going to have what they came for. And we'll talk more about illustrating molecules right now. Okay, to draw a molecule, step 1 is to identify which your central element is and draw it in. If you have 2 elements that are the same, like the 2 carbons, you would draw 2 of them in and put 1 bond between them. Now, you should have some leftover paired and unpaired electrons. The unpaired electrons are the ones that want to bond. So for step 2, we're going to bring in our peripheral atoms so that they line up with the unpaired electrons. Also in step 1, if you, for example, drew nitrogen with its 5 outer electrons, you see that 2 of them were in a pair. And hence we have 3 unpaired electrons representing the 3 bonds that nitrogen wants to form. I did forget to mention 2 things, and that is, there are really 2 rules when it comes to drawing a single element. One is you're only drawing outermost electrons. So let me make that clear. Only outermost electrons are drawn. And then the only other rule is you would put 1 electron as a dot on each of 4 sides before you would pair them up. So if you have 3 electrons, you don't put 2 on one side and 1 on the other. No, you have to put 1 on each of 4 sides before you would pair them up. Okay, after step 2, we're normally done if we only have single bonds, but if we have multiple bonds, then we're going to have to move some of those leftover single electrons in order to form additional bonds between atoms. Okay, on to ionic compounds. In ionic compounds, you have separate ions. Ions are charged species, so we tend to have cations, positive ions formed from metals, and anions, negative ions formed from non-metals. And it should make sense that for somebody to lose electrons, somebody had to gain electrons. And for somebody to gain electrons, somebody had to lose electrons. And we already mentioned that in an ionic compound, we must have charge balance. The number of positives must be equal to the number of negatives. Okay, now the nature of the ionic bond is that it's a bond of the attraction of opposite forces. And the only thing we need to understand about positives and negatives is like charges would repel and unlike charges would attract. So negatives and positives attract. So that tells us why those electrons are going around the nucleus. And it also should tell us why positive ions are attracted towards negative ions. And it would turn out that all positive ions are attracting all the negative ions around them, and vice versa. All the negative ions are attracting all the positive ions around them. Now the form of an ion needs to indicate that charge as a superscript. So here we see the sodium ion with its +1 charge. Sometimes we put in the 1, sometimes we don't. Just like in 1x, we often just leave it as x. Here's the chloride ion and the oxide ion. Oxide's going to have 2 negatives. Sometimes it's written in -2, sometimes it's written as 2 negative. No difference between those. Now we're also going to encounter what are called polyatomic ions, and this is where we have 2 or more covalently bonded atoms that together carry an electrical charge. And here's 2 examples, the carbonate ion and the nitrate ion. Now if we have more than one of these, we would include the entire formula in parentheses and then a subscript outside of that parentheses telling us how many we have. So NH4 is the ammonium ion, and we need 2 ammoniums to balance the -2 charge on the sulfate ion. But you note, 1 sulfate we didn't put in parentheses, 2 ammoniums we did. Now when it comes to our cations, our single element metal cations, they come in 2 different types. One is where we have variably charged metals, which means they can have more than 1 charge. And those transition and intertransition elements often have more than 1 charge. This is one of the repercussions of having their last electrons buried down underneath into a previous shell. But all we need to know is transition and intertransition elements often have more than 1 charge. And so here we can see iron with a +2 charge. We're going to find that's called the iron 2 ion. And iron with a +3 charge, we're going to find that's called the iron 3 ion. And actually we use Roman numerals for those numbers, for the iron 2 and the iron 3. We'll talk more about that when we talk about naming of ions. Okay, now the formulas of ionic compounds, as we've already seen, reflect the balance of positives and negatives. So it's the same procedure we did earlier. I mean, we did our first examples with ionic compounds. And so, as an example, what do they describe the, oh, actually we'll do this example do with some chemical formula determination for ionic compounds in a moment. But first, describe the kinds of simple ions formed by elements of the following groups. In group 1, well, they all have 1 outer electron, which they're going to lose to become like their last noble gas. Losing 1 electron means they have 1 more positive than negatives, for a +1 charge. We're going to find losing electrons you become positive, gaining electrons is how elements become negative. Group 2 elements have 2 outer electrons, and they lose both to become like their last noble gas, so +2. Group 13 lose 3 outer electrons, or 3 outer electrons get to be like their last noble gas for +3 ions. Group 15, well, now these guys want to gain 3 electrons. Gaining negatives makes it a -3. Don't think of plus as you gain and negatives as you lost. Remember, you're gaining or losing negatives. Group 16, like oxygen, forms a -2 ion. If you ever get lost, just grab somebody and ask what's its closest noble gas and how many electrons does it take to get there. So group 17, let's use fluorine. Fluorine is 1 electron away from neon, so it's going to gain 1 electron for a -1 charge. Okay, now some formula determination. What is the formula compound containing the potassium ion and the bromide ion? Well, you're given the charges, so there's your bonding numbers. If not, you'd have to go look at the periodic table to find out. Least common multiple of 1 and 1 is 1, which tells us +1 is balancing -1. So how many potassiums gives us +1? And how many bromides for -1? Next we have what's called the Tin2 ion. Tin needs a Roman numeral to tell us the charge. or somehow we need that, know that charge. And the fluoride ion. Okay, well, let's see. 10-2, bonding number 2. Fluoride, -1, bonding number 1. These come multiple of 2 and 1 is 2, which tells us +2, which takes 2 10s, is balanced by -2, which takes 2 fluorides. Next, we want to know the formula of the compound that contains the iron 3 ion and the oxide ion. Well, those charges are our bonding numbers. These come multiple of 3 and 2 is 6. That tells us +6 is balancing -6. So how many +3 ions gives us +6? And how many -2 ions give us -6? Next we have the lead 4 ion and the oxide ion. That +4 gives us a bonding number 4. That -2 gives us a bonding number of 2. This time the least common multiple is 4. No, not 8. Least common multiple is 4. That 4 tells us what? +4 is balancing -4. We're going to need 1 lead 4 ion for +4 and 2 -2 oxides for -4. If you were thinking we were cross-multiplying, it didn't work this time, did it? If such a simple generalization would always work, I'll share it with you. So don't get in that lazy habit. Essentially, go through these steps and you'll always get the right answer. Okay, let's practice some of the things that we have learned here tonight. First, what is the elemental symbol for silver? Ag. Argentina is named after Argentium, silver. And the element with the symbol Pb, Pb stands for plumum. The ancient Romans made their plumbing from lead. And our protons, neutrons, or electrons found inside of the nucleus. Protons and neutrons. And which of these subatomic particles carries a positive charge? Protons. And which element has 35 protons? Well, let's go get our periodic table and go to element 35. And Br is bromine. And now, what are the number of protons, neutrons, and electrons in silicon 26? Well, do the easy one first. How many protons? And 14. Then, how many electrons? Well, it's not a charged species, so it's also 14. And how many neutrons? Well, the mass number 26 is protons plus neutrons. Subtract out the 14 protons, and that would be 12 neutrons. Okay, what are the number of protons, neutrons, and electrons in the iron 3 ion? Well, protons, look at the periodic table, and iron is element 26, so 26 protons. What does that +3 charge mean? 3 more positives than negatives, 3 more protons and electrons. So we've lost 3 electrons for 23 electrons. Now, can I tell how many neutrons? No, I wasn't given the mass number. And you have to be given the mass number to be asked about the neutrons, or being given the neutrons to ask about the mass number. You have to be given one to be asked about the other. And now, what is the name of the noble gas in period 3? Noble gases, that last column, count down, hydrogen, neon, argon. And the halogen in period 4, which were the halogens again? It was group 17, or group 7A. And period 4 would give us bromine again. Now, how many covalent bonds does nitrogen want to form? Well, it wants 3 more electrons to be like argon, so it's going to form 3 bonds. You get the formula of the ionic compound containing the sodium ion and the sulfide ion. Well, that +1 says bonding number 1. That -2 says bonding number 2. Least common multiple of 1 and 2 is 2, which tells us what? positive 2 is balancing negative 2. So how many sodiums? 2. How many sulfides? 1. Next we have lithium and bromide. Lithium's a +1 ion, so bonding number 1. Bromide's a -1 ion, so bonding number 1. These common multiple of 1 and 1 is 1, telling us +1 is balancing -1. So how many lithiums and how many bromides? Okay, we have the calcium ion, +2 says bonding number of 2. Oxide ion, -2 says bonding number of 2. You note bonding numbers are not signed, so they're always positive. Least common multiple of 2 and 2 is not 4, it's 2. So +2 is balancing -2. So how many calciums? And how many oxides? Again, formula determination is very important, and mastery with this will go a long ways to make your future chemistry much easier. Weakness with this, and this will haunt you. Okay, what is a formula formed from magnesium and fluoride? Well, bonding number of 2, bonding number 1. Again, if you're given the charges, there's your bonding number. Least common multiple of 2 and 1 is 2. So that says +2 is balancing -2. So how many magnesiums? 1. How many fluorides? 2. Aluminum forms a +3 ion, so bonding number 3. Oxide a -2 ion, so bonding number 2. Least common multiple of 3 and 2 is 6. So +6 is balancing -6. So how many aluminums? How many oxides? Okay, aluminum with a +3 charge has a bonding number of 3. Bromide with a -1 charge, bonding number of 1. Least common multiple is 3. So how many aluminums? How many bromides? Okay, that concludes our lecture where we learned about atomic theory, the theory of the particle nature of matter. We learned about the atom, that tiny fundamental particle of matter. We learned about the periodic table, the different parts of the periodic table, meaning the metals and nonmetals, the metalloids, the groups / families, the rows known as periods. We learned about the S block, the B block, the D block, the F block, main group elements, transition elements, intertransition elements, and then we started talking about compounds. We began with molecular compounds where 2 or more non-metals are trying to gain electrons by sharing electrons. That's the covalent bond, the sharing of electrons. And we learned how to determine the formulas of these molecular compounds, the same way as we did the ionic compounds. Ionic compounds are different in that they have opposite charges. We have the cations with positive charges, the anions with negative charges, and we know positives and negatives attract. So that's the nature of the ionic bond, the force of attraction of opposite charges. We learned to illustrate the formulas of ions using superscripts to indicate those charges. So remember that sodium with that elevated +1. And the determination of the formulas of ionic compounds was the same as the procedure for determining the formulas of molecular compounds. And then we finish with a little bit of review, and we are now done.